Continuing from where we left off, let us now look at continuity and connectedness. Continuity and connectedness. Okay. Theorem 4.22. By the way, the solutions are up for the exam. They should be in a file called solutions for exam 1 or exam 1 solutions, something like that. I will also link it on modules. Okay. I've tried to provide the details, but if there are some things that are not there, just fill in the necessary details. Okay. If F is a continuous mapping, if F is a continuous mapping, continuous mapping of a metric space X into a metric space Y, metric space X into a metric space Y, metric space Y, and if E is a connected subset of X, if E is a connected subset of X, then FFE is connected. Okay. Proof. Similar to compact sets, the image of a connected set under a continuous function is connected. Okay. Proof. Assume the contradiction. Assume the contrary. Assume FFE is equal to A union B, where A and B are separated non-empty sets of Y. And B are separated non-empty sets of Y. Non-empty sets. Subsets of Y. Okay. Brief reminder, if you don't remember what separated means, A bar intersection B is equal to phi, and A intersection B bar is equal to phi. Okay? This does not mean that A bar intersection B bar is phi. You can have intersection of their closures, but individually, none of these sets should intersect with the closure of the other. Okay? But G is equal to E intersection F inverse of A, and H is equal to E intersection F inverse of B. Okay? Then G is equal to, then E is equal to G union H, and neither G nor H is empty. Right? Because A and B are not empty. They have some pre-images in F of B, F of E, and they have some non-empty intersection in F of E, so their pre-images is not empty. Okay, since A belongs to the closure of A, we have um, since A belongs to a closure, we have G is a subset of F inverse of a closure. And similarly, well, let me go step by step. And since the latter is closed, because F is continuous, closed as F is continuous, right? It was another property that inverse images of closed sets are closed. It follows that G bar is a subset of F inverse of A bar, right? Therefore, F of G bar is contained in A bar. Right? Since f of h is equal to b, since f of h is equal to b, and A bar intersection B is empty, therefore G bar intersection H is empty. Right? Similarly, G intersection H bar is empty, and this gives therefore G comma H is a separation of E, which is impossible as E is connected. Contradicting that E is connected. Okay, and hence such A and B cannot exist. That means that the image of a connected set was connected. This gives rise to a very important theorem that you have seen before, all of you. I hope, at least. I'd be surprised if you have not. You might not have seen it in this generality, but yes. Let f be a continuous real function on the interval ab. Continuous real function on the interval ab on a comma b if f of a is smaller than f of b and c belongs to R such that f of a is smaller than c smaller than f of b, that is to say it lies between a and b, then there exists a point x belonging to a comma b, a comma b, such that f of x is equal to c. And if you do not recall this theorem, it is called the intermediate value theorem. Intermediate. Right? There are two theorems with names that you might have studied in calculus 2, 1, 2, 3, whatever. mean value theorem and intermediate value theorem. This is the intermediate value theorem. Okay. Note. Similar result holds for f of a greater than f of b. Okay. Proof. Not going into full detail. AB is continuous. It's continuous. And f of AB, sorry, is connected, not continuous. Connected, hence f of AB is connected by theorem 4.23. Okay. 22. Okay. And now the result follows. The result follows from theorem 2.47. I'll just say if such a C did not exist, i.e. if such a C did not exist, such X did not exist, then well, minus infinity to C intersection f of a comma b and C to infinity intersection f of a comma b would be a separation of f of ab. Okay. Remark. At first glance, it might appear that the converse should hold true, right? One might think that the converse holds true. One might think converse holds true, i.e. if there exists X belonging to AB such that f of X is equal to C. Oops. If for every C belonging to such that A is smaller than C is smaller than f of B, there exists X belonging to AB such that f of X is equal to C, then f is continuous. However, a counterexample is as follows. Counterexample. f of 0 is equal to 0, f of 1 is equal to 1, and for everything else, f of x is equal to 1 minus x for every x belonging to 0, 1. Okay, so our so f of x is equal to 0 if x is equal to 0, 1 if x is equal to 1, and 1 minus x if x belongs to 0 to 1. Okay, then every x between 0 and 1, every c between 0 and 1 has a point such that f of x is equal to c. However, this function is clearly not continuous. Okay, so let us talk about the different kinds of discontinuities. This continuities. Okay. What are discontinuities? Uh, Definition: if x belongs to domain of f and f is not continuous at x, then f is said to have a discontinuity at x. Then f has a discontinuity at x. Okay. Now it could happen that f is discontinuous everywhere. Okay. And it is fine. Then f has a discontinuity at every single point x. So even if saying that it has a discontinuity at x makes you feel like, oh, the function is continuous near x, that is not the case. That is still just a definition of what we are going to call. Okay, another definition. Let f be defined on a to b. Okay, consider any point x such that a is smaller than or equal to x smaller than b. Then we write f of x plus is equal to q. This is the book notation. You might have seen seen alternate ways of writing this. If f of tn approaches q as n approaches infinity for all sequences tn in xb such that tn approaches x. Okay. To obtain definition of fx minus, oops, not minus 1, for a smaller than x smaller than or equal to b, consider sequences Tn in a comma x such that, well, such that again Tn converges to t. Okay. Now, it is clear as before that it is clear. Note clear that for x belonging to AB, limit Tn, well, t goes to x, f of t exists if and only if f of x plus is equal to f of x minus is equal to limit t goes to x f of t. Okay. You might be familiar. Note, you might be familiar with these. Familiar with f of x plus is equal to limit x approaches t approaches x from the plus side f of t and f of x minus is equal to limit t approaches x to the minus f of t. Okay. I am using the book's notation for two reasons. One, it is shorter. B, the book is using it. Okay. It is easier for you to go through the book and things if you're familiar with the book notation. Okay. But if you don't want to use this notation, it is fine. Sorry about that. Okay. So now we can talk about discontinuities. Definition that have to be defined on AB. Be defined on AB. Okay. If f is discontinuous, if f is discontinuous at a point x, and if f of x plus and f of x minus exist, then f is said to be, then f is said to have a discontinuity. Discontinuity of first kind slash simple discontinuity. Discontinuity at x. Otherwise, the discontinuity is said to be of second kind. The discontinuity is said to be of the second kind. Okay. Now, there are two ways in which you can have a simple discontinuity. Okay. Note two ways of simple discontinuity. Continuity. Okay. One, f of x plus is not equal to f of x minus. Okay. And second, f of x plus is equal to f of x minus, but this is not equal to f of x. Okay. This is often called removable discontinuity. Discontinuity. Okay. Examples. First, if I look at the function f of x is equal to 1 if x is rational and 0 if x is irrational, then f is discontinuous at every point x, and not just discontinuous, it has a discontinuity of the second kind. So discontinuity, the second kind at every x. Okay? That is because at any point both f plus and f minus do not exist. Right? Given any small epsilon neighborhood, you can always find functions which are 0 and 1, points which are 0 and 1. So if I take epsilon is equal to less than 1/2, so let's say 1/3 or something, you cannot get both the points in it. Okay. Now suppose f of x is equal to x when x is rational and 0 if x is irrational. Okay. This might not seem like a very big difference from the previous case, right? And it's not. It's still a function that's defined on rationals and irrationals separately. However, in this case, then f is continuous at x is equal to 0, and once again has a discontinuity of second kind, and has discontinuity of second kind for every other x. For every other x. Third, let us look at a function which is slightly more complicated. Define f of x is equal to x plus 2 minus 3 smaller than x smaller than negative 2, which is minus x minus 2 for minus 2 smaller than or equal to x smaller than 0, and x plus 2 again for 0 smaller than or equal to x smaller than 1. Okay. Great. Each of these spaces is individually convergent. Okay, so what are the only points where it is not convergent? That's right, not convergent. Continuous. Each of these pieces is individually continuous. What happens at -2? At -2, x plus 2 is 0. Minus x minus 2 is also 0. So even though the functions are not exactly the same, the value is still the same, right? So at -2, the function is matching up. At 0, minus x minus 2 is -2, while x plus 2 is 0. So values do not match up, right? The left limit is -2, the right limit is +2. So you get f has a continuity. Then f has a simple continuity, simple discontinuity at x is equal to 0, and is continuous at every other point. Is continuous at every other point of -3, 1. Right? Since we have not defined sine and not talked about it, I'm going to skip the fourth example. Okay, let's look at now monotonic functions. Actually, let me talk about one more example. Define if x is equal to x if x is not equal to 0, 1 if x is equal to 0. Okay, then f has a simple and removable discontinuity at x is equal to 0. Okay, and is continuous everywhere else. Right? Because if I redefine f of x is equal to 0, then my function would be continuous even at 0. Okay, that's why it's a removable discontinuity. I can just redefine my function to get the correct value. So now let us look at what are called monotonic functions. Okay. Definition. You have seen monotonic functions before in calculus, so this shouldn't come as a surprise for you. Let f be real on AB. That is to say, it is a real valued function defined on interval a to b. And f is said to be monotonically increasing, then f is monotonically increasing. Monotonically increasing on AB if a smaller than x smaller than y smaller than b implies f of x smaller than f of y. Okay, monotonically decreasing, monotonically decreasing if the same condition implies f of x is greater than f of y. Okay, by monotonic functions we mean either monotonically increasing or monotonically decreasing. So this means I'm just copying the above condition, which is a smaller than x smaller than y smaller than b implies f of x is greater than f of y. Okay. Um, Note. Well, let me just write it as a separate thing. We will call them strictly increasing / decreasing if so these conditions are smaller than or equal to or greater than or equal to, my bad, if smaller than or equal to is replaced by strictly smaller than. Okay. Similarly, greater than by strictly greater than. Okay. Theorem 4.29. Let f be a monotonically increasing function on AB. AB. Then f plus and f minus exist. And fx minus exist for every x belonging to AB. Okay. More precisely, supremum of a smaller than t smaller than x f of t is equal to fx minus, which is smaller than or equal to f of x, which is smaller than or equal to f of x plus, which is the infimum of x smaller than t smaller than b, f of t. Okay. Furthermore, if a is smaller than x smaller than y smaller than b, then f of x plus is smaller than or equal to f of y minus y minus. Okay. Similar result hold for similar analogous results hold for monotonically decreasing. Okay. True. Technically, the idea is simple. The proof is also technically simple. It just is a bit long. Okay. The idea is going to be we are going to use the least upper bound property to show that these proper conditions hold. Okay. So, the set of numbers f of t for a smaller than x smaller than a smaller than t smaller than x is bounded above above by f of x, as it is an increasing function. This is a non-empty set, right? And therefore has the least upper bound. And therefore has a least upper bound, which we denote by a, which denote by a. Okay. Well, obviously, obviously, a is smaller than or equal to f of x minus. Oh, sorry, not f of x minus, f of x, right? We want to show a is equal to f of x minus. Okay. So let epsilon be greater than 0 be given. Be given. Okay. Then because a is the least upper bound, then well, as a is the least upper bound, there exists a delta greater than 0 such that a smaller than x minus delta smaller than x, and a minus epsilon smaller than f of x minus delta smaller than or equal to a. Technically, it says that, oh, this should be true for every y in x minus delta to x. Okay, that f of y should be smaller than or equal to between a to a minus epsilon. But for now, we are going to hold this. Okay. Since f is monotonic, f of x minus delta is smaller than or equal to f of t, smaller than or equal to a, for every t in x minus delta, t smaller than x. So we are saying something that is slightly better than the condition I just said. I said that, oh, f of t would have to belong in a minus epsilon to a. What we are claiming here is something slightly better. I'm saying that it has to lie between a of f of x minus delta to a rather than a minus epsilon. Okay. However, what we want is essentially same. Therefore, f of t minus a is smaller than epsilon for every x minus delta smaller than t smaller than x, right? Therefore, f of x minus is equal to a. Similar condition for f of x plus. Similarly for f of x plus is equal to infimum not limited infimum x smaller than d smaller than b f of t Okay, with using the greatest lower bound instead of least upper bound. Okay, now you want to show that these are um, in the following condition, that they are smaller than or equal to um, if a is smaller than x, smaller than y, smaller than b, then because it is, what do you call, monotonic, I have that f of x plus is equal to infimum of f of t, x smaller than t smaller than b is equal to infimum x smaller than t smaller than y f of t. Once again, because it is monotonic, right? And the last equality, sorry, not the last equality, and the last step we need is by showing f of y minus is equal to supremum f of t x smaller than t smaller than p, sorry, a smaller than t smaller than y, which is equal to supremum f of t x smaller than t smaller than y. Okay, and as the supremum is always greater than the infimum, we get this. Therefore, the result follows. Therefore, result follows. Okay, the supremum of any set is always bigger than the infimum of the set. Hence, f of x plus is smaller than or equal to f of y minus. What I said is not very strictly true. The supremum of any non-empty set is strictly greater than the infimum of any non-empty set of the same non-empty set. Okay? An important corollary of this is C-O-R-O-L-L-A-R-Y. C-O-R-O-L-L-A-R-Y. Monotonic functions have no discontinuity of the second kind. Okay? All the discontinuities of a monotonic function are of the first kind. They might not always be removable, but they're always of the first kind. Okay? Then let us show one last theorem. Theorem 4.30. Let f be monotonic on AB. Then the set of discontinuities, then the set of points on points of AB, points of AB at which f is discontinuous is at most countable. Okay. Proof. So there's any monotonic function has at most countably many discontinuities. Okay. We are going to show the result for f increasing rather than f decreasing. It makes absolutely no difference. The proof is really similar, right? Assume without loss of generality. Assume f monotonically increasing. Let E be the set, be the set of discontinuities. Continuities. Okay. Now, if it is discontinuous, we know that it is a discontinuity of the first kind. So both the limit fx minus and fx plus exists. So with each point x of e, we associate a rational number Rx such that f of x minus is smaller than Rx, smaller than f of x plus. Okay? Great. Now since x1 smaller than x2 implies f of x1 plus smaller than or equal to f of x2 minus, we get r of x1 is not equal to r of x2 if x1 not equal to x2. Right? Therefore, this gives us a one-to-one correspondence between the set of E and a subset of rational numbers. Therefore, this gives us a 1-1 correspondence between E and a subset of the rationals, and a subset of rationals which we know is countable, right? And hence this entire set must be countable. Hence the set of discontinuities is at most countable. Okay? I'm going to stop this one here. Okay? Next time we'll look at infinite limits and limits at infinity, and finish off the chapter and move on to the next chapter. Okay? Maybe we'll do some more problems without actually starting off the next chapter. Just have some more exercises and discuss. Maybe I'll just give you a brief idea of derivative and not include that on the exam. Okay, so this will be the last part of tomorrow's limits at infinity would be the last part on the exam. Okay.